We are about to step into a mystery where science meets the unknown. A helium balloon drifts over Antarctica at the edge of space, its shadow sliding across a continent of glassy blue ice and crevassed black seams. Far below, the wind sculpts sastrugi into frozen waves. Above, the sky is so dark it looks like deep water. Hanging beneath the balloon is a ring of radio ears, listening for whispers in a frequency band where the air is usually silent. Then, out of the noise, an electric snap. A pulse, crisp and short, like the click of a cosmic camera. Engineers glance at the polarity, the timing, the geometry. If the signal came from a cosmic ray reflecting off the ice, it ought to be upside down. It isn't. It looks as if something with stupendous energy shot up through the earth, burst into the air, and disintegrated overhead. In a universe where high energy particles are supposed to come down, this one seemed to come up. And if you'd like to help me bring more of these mysteries to life, don't forget to like, comment, and subscribe. Tonight we follow the trail of the ANITA Anomaly. Those unsettling, upward-going events recorded by a balloon experiment at the bottom of the world. And we ask whether we are looking at a portal to new physics or the cleverest mirage the ice can make. The instrument at the heart of the story is ANITA, the Antarctic Impulsive Transient Antenna, a NASA long-duration balloon payload that flies around the continent at roughly 35 to 40 kilometers altitude. Its job is deceptively simple. Sweep the vast, radio-quiet expanse of Antarctica for nanosecond radio flashes. Those flashes can be made in two ways. First, when an ultra-high energy cosmic ray slams into the upper atmosphere and sows a cascade of particles, an extensive air shower. The shower's electrons and positrons are shoved sideways by Earth's magnetic field, and the moving charge emits a faint, coherent radio pulse. Second, when an ultra-high energy neutrino plows into the ice and makes a particle cascade, a brief deficit of electrons inside the shower creates a sharp radio chirp known as the Ascarian effect. ANITA's array of antennas can triangulate the direction and measure the polarization of these pulses to tell air shower reflections from in-ice events. Reflections invert their polarity. Direct, upward-moving signals do not. That difference is the key to the mystery. Across multiple flights, ANITA saw what it was designed to see. Lots of downward-going cosmic ray events, including hundreds of beautiful reflections off the ice. But twice, first in its inaugural flight, and again during its third, it picked up something stranger. Impulsive, cosmic ray, like radio signatures with the wrong polarity for a reflection, arriving at steep angles, roughly 30 degrees above the horizon, as if a shower had been launched from within the Earth and was rocketing up into the sky. The reconstructed energies of order and electronvolt were not shy. If these were ordinary cosmic rays, they had done something impossible by punching through a planet. If they were neutrinos, they had traversed the Earth without being stopped, and then somehow triggered a shower, emerging at an angle too steep to be expected. The collaboration wrote them up with care. Upward-going, cosmic ray-like events whose properties didn't match the easy explanations. To feel how shocking this is, we need a quick map of what even rare particles can and cannot do. Cosmic rays are energetic nuclei, protons and heavier ions, that slam into our atmosphere from above. They do not cross the Earth. A single meter of rock is enough to stop most of them. Neutrinos are different. They ghost through matter so effortlessly that trillions pass through your body every second, mostly without a trace. but at electron-volt energies. The energies ANITA can hear. The Earth is no longer transparent even to neutrinos. Probability catches up with them. At these energies, a tau neutrino can occasionally skim the planet, interact near the surface, produce a short-lived tau lepton, and that tau can pop out and decay in the air, making an upward-going shower. That is a known standard model channel. The catch is geometry. At EeV energies, the Earth is so opaque that only very shallow Earth-skimming trajectories are plausible. Showers bursting out at approximately 25 to 35 degrees above the horizon are strongly disfavored. The two ANITA events did exactly that.
If you try to make the numbers work by dialing up the diffuse flux of tau neutrinos, so that by chance a few make it through and burst out steeply, you run into an immediate wall. Experiments like IceCube at the South Pole and the Pierre Auger Observatory in Argentina, which are also sensitive to ultra-high energy neutrinos in their own ways, had not seen the accompanying flood of events you would expect. Analyses comparing what ANITA reported with what IceCube and Auger could have missed conclude that a simple, diffuse tau neutrino explanation overshoots existing limits by orders of magnitude. In plain language, if the ANITA events were just ordinary tau neutrinos, we should have seen many more elsewhere. And we haven't. So we have a fork. Either ANITA stumbled on a new kind of source or a new kind of particle, or something in the Antarctic environment, or the instrument tricked us. Both branches have been explored with vigor. First, the conservative branch. Could ANITA have mistook a reflected downward-going cosmic ray for an upward-going one because the reflection off the ice sometimes fails to flip the signal's polarity? Under normal conditions, an air-to-ice reflection inverts the electric field. But real ice is not a single, flat mirror. It is layered, with buried horizons of density change. It has roughness, crevasses, and subglacial lakes. Radio waves can reflect from interfaces below the surface and scatter in ways that complicate polarity. Several studies have asked whether unusual subsurface reflections, say from a buried internal layer with a lower refractive index change or a geometry that involves multiple bounces, could produce a non-inverted pulse that mimics an upward shower. It is not impossible in principle. Whether it can explain the exact shapes, times, and directions of the ANITA events is still debated. But the ice mirror hypothesis is one of the most persistent, mundane contenders. Another conservative idea invokes transition radiation. When a particle cascade crosses the boundary between ice and air, the sudden change in dielectric environment generates a radio pulse. If a cosmic ray shower, or a neutrino-made shower within the ice, happened to intersect the surface in just the right way, maybe the transition pulse could look like an upward event. Detailed simulations built specifically to handle showers traversing the ice-air interface suggest that transition radiation cannot reproduce the observed signals once realistic geometries are enforced. The signatures don't line up. What about the social solution? Anthropogenic noise. Antarctica is famously quiet in radio, but human-made emitters exist. Bases, aircraft, even devices on the ice. ANITA's pipeline is designed to veto such sources using direction, polarization, and waveform features, and the events in question looked remarkably like natural air showers in their shape and spectral content. That doesn't absolutely exclude a rare human glitch masquerading as nature, but it makes it an unsatisfying answer without a specific culprit. Now the adventurous branch. If the signals are real upward-going showers at steep angles, Perhaps standard model neutrinos are not the messengers. Could there be a new, feebly interacting particle that crosses the Earth easily and then converts near the surface into a tau lepton, or something that decays into a shower? Physicists have sketched many possibilities. Sterile neutrinos that mix with ordinary ones just enough to peek back into the visible world. Long-lived dark sector states that travel far before decaying. Exotic leptoquarks or supersymmetric partners that change the interaction bookkeeping. The appeal of these scenarios is that they can be tuned to make Earth less opaque to the relevant particle, while keeping most of existing data intact. The danger is that the same knobs must then pass constraints from colliders, other neutrino experiments, and cosmic observations. It's a tightrope walk in parameter space.
A different twist is to relax the assumption that the incoming flux is diffuse. What if ANITA saw bursts from a bright transient astrophysical source? Say, a flaring blazar, a tidal disruption event, or an off-axis gamma-ray burst, so intense that rare steep angle events became likely for a brief time. Teams went looking for partners. IceCube searched its sky for neutrino activity coincident in time and direction with ANITA's events, and found no significant coincidences. Nothing bright enough showed up in gamma rays either. The absence of multi-messenger partners doesn't kill every transient model, but it tightens the belt considerably. As the debate churned, ANITA flew again. The collaboration reported additional upgoing ultra-high energy candidates in its fourth flight, keeping the puzzle alive. Meanwhile, theorists and experimentalists asked a more global question. Are the ANITA events self-consistent once you fold in everything we know from other detectors? A 2023 analysis combined internal consistency checks with the stark fact that IceCube, which has operated for over a decade under the same sky, has not seen an equivalent population. The conclusion was sobering. If you bake in what IceCube should have detected, many of the new physics escape routes shrink or disappear. That isn't the end of the story. Some clever models survive, but the room is smaller. More recently, the Pierre Auger Observatory, the world's largest cosmic ray detector, tackled the question from another angle. If you normalize an upward-going flux to match what ANITA saw, Auger should have recorded many events in his target energy range by looking for very inclined air showers that rise rather than fall. It hasn't. The latest analysis argues that interpreting ANITA's anomalous pulses as a steady flux of upward-going showers is in strong tension with Auger's non-detections. That pushes the steady flux options further to the margin and puts the spotlight back on rare systematics, exotic transients, or genuinely new physics with very special properties. At this point, the problem resolves into a handful of live possibilities, each with pros and cons. 1. Subtle Earth optics. Antarctica is not a billiard ball. It's a living icescape that can guide, refract, and reflect radio waves in ways that defeat simple models. If rare geometries can occasionally flip the up-down signature without breaking other telltales, we shouldn't be surprised that a balloon experiment skimming a continent-sized mirror catches one or two in a flight and never again. The downside: reconciling all observed features with such tricks has proven hard. Multiple teams have chipped away at this, and while it remains plausible, it's not a slam dunk. 2. New messengers. A feebly coupled particle that sails through the Earth and then decays near the surface is an elegant way to get steep emergence angles. It would be a watershed discovery, evidence of physics beyond the standard model from a balloon over ice. The downside is the burden of proof. Any proposed particle must dodge constraints from accelerators, cosmology, and other astrophysical messengers. The more knobs you add to dodge the walls, the more the explanation can begin to feel like a story tailored to a handful of events. 3. Transient fireworks. An explosive source could have lit up the air in the right direction at the right moment. Multi-messenger astronomy is built to catch such coincidences. The problem is, we didn't see the friends we expected. No neutrino clusters in IceCube, no obvious flash and gamma rays. That doesn't kill every scenario. Some sources are beamed or hidden, but it trims the tree of possibilities.
4. A trick of transition radiation or instrument response. Detailed simulations now disfavor the simplest transition radiation mimicry. The instrument has passed many other reality checks. That doesn't mean an unknown systematic is impossible, just that it must be both subtle and selective. Part of what makes the ANITA Anomaly so enthralling is that it sits at the seam of disciplines. To untangle it, you need high-energy particle physics to predict interaction probabilities, atmospheric physics to model air showers, glaciology to understand the ice's radio properties, electrical engineering to calibrate antennas, and astronomy to cross-check the sky. It is a puzzle that demands humility, because a small misstep in any one of those arenas can masquerade as a miracle or smother one. It also forces us to confront how science advances at the frontier. The most exciting discoveries often begin as outliers, odd points on a plot that won't sit down. If you're too strict, you erase them as noise and miss the revolution. If you're too eager, you build castles of theory on anomalies that later wash away. The ANITA team did what good explorers do. Report the oddity with all the context they can, invite the world to poke it, and fly again. Other teams did what good neighbors do. Test the consequences with their own instruments, prune the easy trees, and leave the hard ones standing. The result is not a neat headline. It is a narrowing funnel of truth. Whatever the resolution, ANITA has already taught us something profound. It has demonstrated that radio is a powerful, scalable way to hunt for ultra-high energy neutrinos over continent-sized detectors made by nature. It has pushed us to refine how we understand radio reflections from layered ice, right down to the polarity flips. It has tightened the partnership between the balloon and the stratosphere, the cubic kilometer of phototubes embedded in Antarctic ice, and the surface arrays on another continent. And it has reminded us that a negative result, a ruled-out explanation, can be as valuable as a positive one when you are mapping territory no one has walked before. There is, too, a philosophical tremor in the idea of a particle clawing its way up through a planet. We like our arrows to point down. Gravity pulling, rain falling, particles raining in from the stars. An upward bolt contradicts that intuition, and that is why it catches the imagination. If the ice played a trick, it's a beautiful one. A lesson in how the world's surfaces can fold signals back on themselves. If nature slipped us a new particle, then the universe is wider today than it was yesterday, and a balloon over Antarctica was the first to hear it pass. As we leave the balloon circling its lonely path, the radio ears still cocked to the ice, think of the improbable infrastructure that makes this kind of mystery possible. The logistical heroism of Antarctic campaigns, the patience of analysts combing through false triggers for a handful of real snaps, the coordination needed to ask an observatory at the South Pole and an array in Argentina to check another experiment's ghost. Whether ANITA's upward flashes turn out to be a mirage or a messenger, the process has already worked as designed. The universe whispered, We argued about what it said. We built better ears. So here's the question I'll leave with you. If you were in the control room and another upward-going pulse lit the screens, clean, steep, undeniable, what would you bet on now? A sly echo from Antarctica's layered mirror, an astrophysical firework caught at just the right instant, or a particle the textbooks do not yet admit? Tell me why in the comments, and what test you'd run next to turn belief into knowledge.